In this video I use this interferometric setup, which you can see about in previous videos, and I'm measuring the flicker noise of this stepped attenuator from Hewlett-Packard. It's set to 2 dB attenuation, and I will compare it to other attenuators that can also be set to 2 dB. The main spectrum of Linrad clearly shows that there is flicker noise, these noise things on the side of the signal, if you compare with the previous video. I am injecting a signal at the separation of 10 Hz. I have to use this 8657B because that is the only one that can step in steps of 1 Hz. The other ones go 10 Hz. So I have a signal here 10 Hz away, and I set it at -70 on this graph. That's quite some time ago, but it has been fairly stable. So it shows -70.1. And I click on the signal, and we will see it should show now 0. And here. And indeed it does. So I want to see that signal at -70 here in Linrad. And this is an old reading, but I will make it fresh now. And it has stayed properly calibrated. So I switch off that generator and wait for a while to get the sideband noise at the separation of 10 Hz. I think you can see here. The separation is 10 Hz and the bandwidth is 1 Hz. And I will have the noise floor here fairly soon. So I read -165.4 dBc per Hertz. It is already 1 Hz bandwidth. I have tuned the balancing of the interferometer much better, something like 20 dB. And then the noise is a little lower. Here. Oops. -170.6. And it's clear this was the previous measurement. I had some problems. And here the carrier is fairly weak. And it's of course drifting very slowly. We can see from the noise here it was stronger, and now it is significantly lower. But balancing even better than this will not make any difference. And we can see easily the flicker noise here. This is another 2 dB attenuation. There are occasional noise bursts, as you can see here. You can see it all the way out. I have not been in the room while this has been recorded. The noise level I see is -175.5. And balancing is quite good. And here is the label on the other side of this attenuator. This is the next one. Can I read? JFW Industries. and I can clearly see flicker noise here, and you can see it is much noisier than the good one. And I read the noise floor here. Well, minus 173.6. This is my oldest stepped attenuator. I can no longer read what model number or who made it, but I can see Plymouth, England here, and attenuator at what the model number might be, I don't know. Anyway, it's set for 2 decibels. One of the 2 dB switches is switched in. It has some flicker noise, but not so much. I can read here. Well, I couldn't. Sorry. It looks a little unstable, but some kind of average reading is minus 171.5. I will switch a couple of times back and forth to see if that makes it more stable. Getting good statistics in the bandwidth of 1 Hertz takes a very long time, so I will be happy with this once I can read it. There is this bug in Linrod. I have tried to find it, but not successfully as yet. Well, here is the result. Minus 172. That's pretty close to what I saw before, but it now looks a little bit more regular now. So that's probably just variations of the noise. This is another one from JFW Industries. I have not been using this one for at least 3 years, and you can see it is unstable. I will rotate it back and forth many times and then try again. The second one from JFW is minus 174.2. Looks like that, and we can see the flicker noise and also some instability. This is a tech scan, and the model number is SA50, and of course set for 2 decibels. I can see some flicker noise and occasional, but maybe that's because I'm talking too loudly, so forget about that. The noise floor is here, and I have to wait a little. The noise floor is at minus 174.2. And of course, when I talk very loud, you can see there is a problem. This is a fixed attenuator with SMA connectors on it. The noise is minus 171.1. I know from before that this one is very noisy. And now that is very visible here. The flicker noise is horrible and extends far away in frequency. The level is minus 152.3, and that is a 10 Hz separation. Here are two series connected 1 dB attenuators. And here is the pair of two 1 dB SMA attenuators, 176 and 0.4, and it looks pretty good here. And here. I connect the spectrum analyzer here. This is from where the power comes into the test object. So the carrier level in this series of measurement has been plus 27 dBm. I want to show something about the balancing. To that end, I make things faster. And then make the bandwidth greater. And here is what remains of the carrier. It is 105 dB below the full carrier power of one arm of this interferometer. And you can see it's drifting. This is typical. Here it looks like on the oscilloscope, and I turn the fine tuning knob here for amplitude. And that is pretty difficult, but I can do it. And then I have the phase fine tuning back there. And it's equally difficult. And you can see how it drifts fairly rapidly. I was down at about 114 dB or so. And I can see here how it slowly increases. It's easier to tune with this tool, like this. Well, something like that, and also on the phase knob. Difficulty is when moving that tool away. Anyway, stability is a problem, as you can see here. On the other hand, I don't need this extreme balancing. Even with the very best things, this is by far good enough. Because the oscillator I'm using is pretty good, it doesn't produce much noise. And you can see this works well enough, I think. Here is a collection of what I have found in this study. The interferometer only, as I looked at in a previous video, at 10 Hz, it is at minus 175 approximately. It means that values very close to that. This one is obviously below, but also here and maybe these ones, are so close to the limit of the test system I have that the result is not significant. But this applied research HF50 at -152, it is really very noisy and it is very significant. And also other things, -170 for the Hewlett-Packard 355C. It's an obvious contribution from that attenuator. And also the stepped attenuator, the old one at 172, that is high above the system at 175. And these fixed in MET 6462, they are also pretty noisy. So these are the results, and one has to be a little bit careful about using attenuators when looking for extremely low flicker noise in a system. Probably this is well known to all the professionals, but to me this is interesting new information. Particularly that there could be very noisy attenuators, this one, that would affect performance of a system into which it is inserted.